Good morning, class. I am Dr. Ezekiel, and I'll be taking you Introduction to Food Technology, the food process engineering aspect. I want to believe that you have had a feel of what food technology is with my other two colleagues who took you in food microbiology as well as food chemistry. First of all, I want to disabuse your mind as to what food process engineering is all about. Most of you have the impression that it's calculation and you can't pass it or you can't score high in it. That is not true. You can actually get, if the whole mark allotted to it is 100, is 20, you can actually get the whole 20 marks because it's based on principle and not on how the lecturer is feeling, what he or she feels about your writing or your write-up. Once you follow principles regarding the calculation aspect, you have your full mark. And I'll be starting with the scope of food process engineering, concerned with the design and integration of the series of manufacturing stages, which result in the transformation of the raw material to the finished product. And if we now have to apply this to food process engineering, the only two things that will change are you need to define the raw material. You also need to define the finished product. As far as raw material is concerned, for food process engineering, the raw material is agricultural produce or agricultural raw material, and the finished product is going to be food product. In other words, you can define food process engineering as basically concerned with the design and integration of the series of manufacturing stages, which results in the transformation of an agricultural material to food or food products. The raw material in this case is agricultural material, and the finished product in this case is food. There are about 3 major important criteria that are supposed to be considered when you are talking about process design. The first one is that the process must produce both the product and any byproduct at the required specification. In this wise, when talking about byproducts, it does not necessarily mean something useful. It can actually be a waste product as well. But all of these must be produced at required specification. For instance, in the production of curry, you must know what is the weight of the cassava you started with, what is the weight of the final product, which is gari, that you ended up with, what is the weight of water that was extracted during the process. You must know the weight of the peel. All these are supposed to be byproducts, but they must be produced at required specification. When the product is not yielding much and the byproduct is yielding much more than the product, you already know that you are going outside your specification, then that process needs to be redesigned. Secondly, the process must be reliable and efficient, both in its own operation and in continuity with preceding and succeeding process. What is meant by that is that you must be able to reproduce it anytime, and also in relationship to other processes that has come before it or is coming after it. It must be efficient. No time wasting, no wasting of materials. And thirdly, the overall processing cost should be kept to a minimum. You don't produce to run at a loss. You produce to make gains. And you try as much as possible to keep your processing costs to the barest minimum so that you don't produce or or process beyond what is what you can actually manage. Other people are in the market and they too they are fixing their cost price. If they are able to make gains at very low cost price, you too should be able to produce at very low cost price, at very low processing cost, so that you can compete favorably with others in the market. However, this should not be at the expense of quality. Study of food process engineering is an attempt to analyze all forms of physical processing in the food industry into a small number of basic operations, which are called unit operations. Although the food process industry is a combination of diversified, complicated, and differing processes, the essential concept is to divide physical food processes into basic unit operations, each of which is unique and dependent on coherent physical principles. Some common unit operations in the food industry are for solids. Examples include screening, size reduction, weighing, and blending. While for fluids, which includes both liquids and gases, examples are sedimentation, evaporation, distillation, bleaching, crystallization, agitation, membrane separation, gas absorption, filtration, and fluid flow units. There could also be general operations such as heat transfer and reaction. And dimensions, with emphasis on the SI unit. Engineering measurements consist of 3 parts. The first part is the dimension of the quantity. The second part is the unit, which represents a known or standard quantity. And the last part is a number, which is the ratio of the measured quantity to the standard quantity. Dimensions. To talk about the first part. Dimension. This is the first aspect of engineering measurement. There could be fundamental dimensions and there could be derived dimensions. Fundamental dimensions are the basis of derived dimensions, and they include length, mass, time, temperature, and for engineering, a derived unit called force. These dimensions are represented symbolically with length, which is L in square brackets, mass, capital M in square brackets, time, capital T in square brackets, force, capital F in square brackets. The derived dimensions are expressed in terms of these fundamental dimensions. Examples of derived quantities are area, which is a combination of length times breadth, both of which are length under fundamental dimensions. So we have L square brackets raised to power 2, volume, length times breadth times height, which is L square brackets raised to power 3, velocity, which is distance over time, which is L over T in square brackets, pressure, force over area, which is F in square brackets over L in square brackets squared. We also have density, which is mass over volume, M in square brackets over L in square brackets cube, energy, which is force times distance, which is F in square brackets times L in square brackets. Dimensions are measured in units. Dimensions are units. A unit is a term used to designate or indicate the size or amount of a quantity of a certain dimension. Examples include inches, feet, meter, centimeter, millimeter, micrometer. All of these are units of length, a fundamental dimension. In order to facilitate comparison, these units have been defined in terms of physical quantities. In some instances, it could be meter, it could be seconds, it could be degrees Celsius with respect to temperature. For instance, meter has been defined as 1,650,763.73 times the wavelength in vacuum of the radiation corresponding to the undisturbed transition between 2p10 and 5d5 of the atom krypton 86. Unit system. There are 5 unit systems which have been used over the years. These are the foot-pound system, which is referred to as FPS, the centimeter gram second, which is CGS system. We also have the British engineering system, American engineering system, and the commonest one is the Système Internationale des Unités, which is most commonly used nowadays, usually referred to as SI unit system. Table 1 expresses the 4 fundamental dimensions in food process engineering with their units under the different 5 unit systems. Row 1 expresses the units for the 4 fundamental dimensions for CGS, while row 2 expresses same for FPS. Row 3 expresses same for British engineering. And as it continued, the next row has to do with American engineering, and the last row, SI units. It should be of note that 1 pound weight equals 32.2 pounders, and 1 slug equals to 32.2 pound mass. There are several benefits of units in engineering problems. A little will be mentioned of some. It reduces the possibility of inadvertent inversion of any portion of the calculation. 2. It reduces the calculation in many cases to simple ratios which can be easily manipulated. 3. It reduces the intermediate calculations and eliminates the considerable time in problem solving. Unit also enables the students to approach the problem logically rather than by remembering a formula and plugging numbers into the formula. And 5th is that it demonstrates the physical meaning of the numbers in the problems. Dimensional consistency. In all engineering calculations, all equations must be dimensionally consistent. What this means is that each term on both sides of an equation must represent the same kind of quantity and thus reduce to the same dimensions. Also, dimensions can be handled algebraically and therefore they can be divided and multiplied. In engineering calculations, in order to ensure dimensional consistency, a dimensional factor GC, which has the same numerical value as g, the acceleration due to gravity, has been introduced. This means that its value varies with the system of units. Generally, F, which is force, is directly proportional to mass and acceleration of a body, and therefore a proportionality factor K has to be introduced in order to equate F to KMA. This proportionality factor K has the units of force, time, mass, and length, and it is the reciprocal of GC. So in the FPS system, where the unit of force is in pound-ounce, mass is in pound mass, length is in foot, and time in seconds, therefore the unit of K is as displayed is the inverse of the unit of K as expressed in the slide shown. The unit of K and GC, which is 1/K in American engineering system, likewise in CGS system, as well as in SI unit system. The showing is the unit of K and GC, which is 1/K in British engineering system. Dimensional ratio. Expressing quantities in ratio gives one a comparative idea between the quantities in question. These ratios are always dimensionless. Dimensionless ratios are often used in process engineering, comparing the unknown with some well-known material or factor. Example of dimensional ratio, which is dimensionless, is specific gravity. Specific gravity is a ratio of density of any substance assuming the substance A to that of water. This gives rho A over rho water, which is density of substance A, divided by the density of water. Now, dimensionless ratios are used frequently in the study of fluid flow, mass, and heat transfer, all of which are important basic operations, earlier referred to as unit operations during food process engineering. We will be moving to another major topic, which is precision of measurement, scientific notation, and significant figures. All physical measurements carry some degree of precision. The statement of quantity should either itself imply the tolerance, or else the tolerance should be explicitly specified. For example, 10.1 plus or minus 0.05 meters means that the length measured could be between 10.15, that is 10.1 plus 0.05 meters, and 10.05 meters, and that is 10.1 minus 0.05 meters. The precision of the result from any mathematical manipulation should be noted that it cannot be better than that of the initial measurement. A very relevant example of the last statement is in the calculation of the volume of a tank with the following dimensions: radius 2.550 meters, height 10.0 meters, volume. The formula for volume is pi r squared h, which is 3.147 times 2.550 squared times 10.0. With a calculator, the answer obtained will be 204.282, where the units will be meter cube. But the correct answer is actually 204 meter cube. Why? Since the least precise quantity is the height, and it only has 3 significant figures. It only has 3 significant numbers. Therefore, the result from any mathematical manipulation cannot be more precise or better than that of the initial measurement. The correct answer has to be corrected to the least precise quantity in the calculation. Significant figures. The significant figures of a number are the digits from the first non-zero digits on the left to either A, the last digit, 0 or non-zero on the right, if there is a decimal point, or B, the last non-zero digit of the number, if there is no decimal point. This is a rule of thumb that needs to be remembered anytime significant figures of a number are to be determined. Examples on significant figures are as shown. Take note of how they have been converted first to scientific notations. And once you have been able to convert it to a number to scientific notation, it makes it easy to locate or easier to define the significant figures in that particular number. You can see examples on 2300 having two significant figures, 2300.0. Because of the decimal point, the digit after the decimal must be considered, therefore giving 5 significant figures. We have 23040 having 4 significant figures. Applying to U diligently, 0.035 has 2 significant figures. 0.03500 has 4 significant figures. Note, the number of significant figures in a reported value of a measured or calculated quantity provides an indication of the precision with which the quantity is known. The more significant figure, the more precise is the value. Another major topic under food process engineering is process and process variables. Process. What is a process? A process is any operation or series of operations that cause a physical or chemical change in a material or mixture of materials. Example is concentration of orange juice. The material that enters a process is referred to as the input or feed to the process, and that which leaves is called the output or product. A process unit is an equipment or apparatus in which one of the operations that constitute a process is carried out. Each process unit has associated with it a set of input and output process streams, which consist of materials that enters and leave the units. Now, process variables. Process variables characterize a process which can either be measured or calculated. Some of these are mass, volume, density, concentration, and pressure. Density. The density of a substance is the mass per unit volume of the substance. Density of pure solids and liquids are relatively independent of temperature and pressure and may be found in standard texts such as Chemical Engineering Handbook. Density of mixture of liquids can be estimated by assuming that the component volumes are additive. The formula above shows that N is the number of components in the mixture, while I is the density of the ith component, and Xi is the mass fraction of this component. This formula works best for mixtures of components with similar molecular structures. The specific gravity of a substance is the ratio of the density of the substance to the density of water at a specific condition. specific gravity equals rho of that so of a specific substance to the reference, the rho ref, which is the density of the reference substance, which you usually know, where the reference density is the density of water at 4 degrees C. We can have different values depending on the system of units that is being considered.